Hello, we are in lesson 5 corresponding to Gauss's law. In the introduction, we saw the concept of flux, and then we stated Gauss's law. Today we are going to apply it in a problem to calculate the electric field corresponding to a linear charge distribution. But first, let us recall that Gauss's law tells us that the electric field flux through a closed surface is equal to the net charge enclosed inside it divided by the electric permittivity in the vacuum epsilon sub 0. Its mathematical expression is the one shown on the screen. The flux corresponds to the surface integral of the scalar product between the electric field and the differential vector of S. This flux is equal to the enclosed charge divided by the electric permittivity in the vacuum epsilon sub 0. In the drawing, we have depicted a closed surface corresponding to the Gaussian surface, enclosing a point charge Q. At point P, a differential surface element has been chosen, and the two vectors with which we are going to work, the electric field vector and the differential vector of S, which is a vector perpendicular to the surface at that point and outward. Gauss's law is used to calculate more simply the electric field created by distributions with symmetry. In this case, we are going to calculate the electric field created by an infinite rectilinear linear distribution of density lambda coulombs per meter, that is, an infinite wire. We are going to calculate the field at a point P located at a minuscule distance r from the distribution. The steps to follow are as follows. First, we must ask ourselves what the structure of the electric field we are looking for is like, that is, what the field lines are like. Then we will choose a suitable Gaussian surface, which has to be an equipotential surface. Then we will calculate the electric field flux through this surface and see what charge it encloses. And finally, we will apply Gauss's law to clear the modulus of the electric field we are looking for. Well, let's start with the first step. We ask ourselves, how is the structure of the electric field that creates that infinite wire? In this case, it has cylindrical symmetry. Therefore, the field lines are radial and perpendicular to the wire. In this image, we see the wire from above and observe the field lines that are radial. On the right, we see the representation in 3 dimensions and observe that the electric field is contained in a plane perpendicular to the wire. The modulus of the electric field will depend on the distance or minuscule to the center, to the distribution. Next, we are going to choose a Gaussian surface. It must be an equipotential surface. Recall that equipotential surfaces are those to which the electric field is perpendicular at all points. In this case, since the electric field is radial, the equipotential surfaces will be cylindrical surfaces of infinite length. As the Gauss surface has to be a closed surface, what we are going to do is to choose that cylindrical surface of length h and put 2 covers on it, one upper and one lower, surfaces 1 and 3. These circular surfaces of radius r are complementary surfaces through which the flux is 0. Why is it null? Because if we observe, for example, surface 1, at any of its points, the differential vector of S and the electric field vector are perpendicular, and therefore this scalar product is 0. The same would be true for the lower stage. Next, we will calculate the electric field flux through the chosen Gaussian surface and see what charge it encloses. The total flux will be equal to the flux through surface 1 plus the flux through surface 2 plus the flux through surface 3. As we have seen, that through surface 1 and through surface 3, that is, through the lids, the flux was 0, we are left with only the flux through surface 2, through the side surface. In this case, if we choose any of the points on this surface, we can observe that the differential vector of S and the electric field vector are parallel. Therefore, the scalar product between these 2 vectors is equal to the product of the moduli. Thus, the total flux is equal to the integral of the product of the modulus. It is also true that in any of these, all points on this lateral surface are at the same distance or minuscule from the wire. Therefore, the modulus of the electric field is constant and can be left out of the integral, leaving the flux equal to the modulus of the electric field times the area of this side surface, SII, which is equal to 2pi times r times uppercase H. The charge enclosed by the Gaussian surface is lambda times the length h of the cylinder. Finally, let us apply Gauss's law, which tells us that the flux, which we have just seen to be E times 2 pi RH, is equal to the enclosed charge match epsilon sub 0. Since the enclosed charge is lambda times h, the h's go away, and we are left with the modulus of the electric field being lambda split 2 pi epsilon sub 0 r. To give the vector character to the electric field, we multiply it by the unit vector u sub r, which is a vector of modulus 1 and radial direction. Finally, I wanted to plot the modulus of the electric field created by the linear charge distribution of lambda coulombs per meter as a function of the minuscule distance r to the wire. We can see that as we move away from the wire, the electric field decreases. And that's all. Thank you very much for your attention, and see you next day.